So this is Unit 5. Unit 5 is looking at circular motion, stuff that moves in circles. And then we're also going to combine universal gravitation and orbits into this as well, because it turns out one leads naturally to the other. By the end of this unit, yes, you will have done rocket science. Okay? This is, was that a phone that went off? No? Okay. Now, this is the biggest unit test of the year. This, not momentum, this one. I think it's worth 16%. I don't want to call it the toughest as much as it's a lot of new material. The best message I can give you for this unit, I know up until now, many of you have been sloughing the homework and then cramming the homework in right before the test. This is when that'll start to kill you. Keep up with the homework, all right? What we're going to do is we're going to spend about 4 lessons looking at the properties of circular, or fancy word, centripetal motion. And then we're going to try and link it to gravities and orbits. And so we start out with the question. Miller, can you read to me example 1? What's the question? Is it possible for an object to have constant speed but also be accelerating? What do you think? Jake says no. Josh says yes. Convince me. Well, you know what? Really, the no argument is hard to prove. To convince me, all you have to do is give me an example of something that is moving at a constant speed but also accelerating. Can you give me an example of something? Yeah. Alon. What? Because all vectors have 2 components. They have magnitude and what? So if the magnitude, the speed isn't changing, what can be changing? Direction. Changing direction. Moving in a circle is a great example, Alon, a terrific example. Did you come up with that, or did you clue in because we're talking about circles and blah, blah, that? Very well, okay? So, now, we're going to be careful. If we're moving in a circle, we are going to be moving at a constant speed. It is possible to have a changing speed while moving in a circle. Carl, that leads us to what we call Ukhimath. Although, if you take physics next year, probably you'll be able to handle it, okay? For now, we're going to move in a circle. We're going to allow the direction to change, but we're going to keep the speed constant. You know what? We're talking about something like this. So for an object moving at a constant speed in a circle, and what we'll call that is uniform or constant circular motion, its velocity is changing because its direction is changing. Oh, and if your velocity is changing, you must be accelerating, because that was the definite acceleration was a change in velocity over a given time. This is the most important fact to keep in mind about circular motion. The object is accelerating. Oh, and if you're accelerating, there must be a net force, because F equals m is Newton's laws. The acceleration is not 0, so there must be an unbalanced force. And that's what we're going to spend a lot of time looking at and talking about. Now, first of all, we need to define the direction of the velocity. Turns out when you're moving in a circle, well, pause the video again. The velocity, here's what we say, tangent to the radius. Tangent is a fancy word for perpendicular to. Okay? It's called a tangent line, but as I lamented the other day, you guys don't do much geometry in the pre-calculus stream anymore. In the principal stream, all the kids had seen a tangent line, and they would say, oh yeah. Now, those of you in calculus know what a tangent line is, just kisses, barely touch. That's what we're saying with the velocity. To find the direction of the acceleration, we're going to perform a vector subtraction. So for constant acceleration, Vf equals Vi plus At. So if you solve for A, it's Vf minus Vi over T. And I'm going to do that with vector math now. But I got to be a little technical. We're soon going to show that the acceleration isn't quite constant, so this relationship is only true for a very small time interval. Just, okay. But we can at least, because time is a scalar, the direction is going to come from the subtraction of the vectors. How do we subtract vectors? We don't. We have the opposite. So on the next page, it says, find the direction of the acceleration by subtracting V final a split second later from V initial. So here's my high-tech picture. V final is like 1/100th of a second later. It's right there. Okay, it's going to be this plus negative V initial. The resultant is if I draw it here, here is negative V initial. The resultant is what direction? Toward the center. Toward the center. And this is a counterintuitive concept. I'm going to assume all of you have been on some kind of a ride or a car that was moving in a circle and you felt like, oh, I'm getting pushed outwards. I must be accelerating outwards. You're not. If you are moving in a circle, you're accelerating inwards. You're accelerating inwards. You're accelerating inwards. What's the acceleration direction if you're moving in a circle, Anthony? Toward the middle. In fact, we're going to have a special word for that. So we see an object that is accelerating towards moving in a circle is accelerating towards the center of the circle. In fact, we say it is he already has, thanks. Center seeking. There's a Latin word for center seeking. Centripetal. Centripetal. We say it is a centripetal acceleration. Example 3. This is a top view. Suppose you had a ball on a frictionless tabletop and it's rolled along this circular track as shown. When it leaves the track right here, which path will it trace out? Path A, due to the fact that the ball has some circular momentum and it wants to keep going in a circle. Path B, since there is no force on the track when it leaves and the object should go in a straight line. Or path C, since when the track is no longer supplying a force on the ball will fly outwards. What do you think? You know what? Once again, we haven't done this for a while, we're going to vote, and how high you hold your hand up is how sure you are of the answer. Who says, it's got to be A, Mr. Dueck, it's going to keep going in a circle? Cole's just, okay, no, we got one. Okay. B, Mr. Dueck, it's got to be B, because that has like physicsy words in it. Who says C, because I've gone on a merry-go-round and I know when I let go, I go flying outwards? Who's been on a merry-go-round playground ride before? It's one nearby, right? One just a couple of blocks that way, I think. Pardon me? Called Lions Park. It's not a good one. I would almost do a walking field trip there, but I've walked there myself. If it was a nice big one that could support your almost adult weights, I would totally go there because there's some beautiful stuff you can do. But it's not a very good one, unfortunately. Okay? So one person said that. Well, it turns out, now why is that correct? For it to be changing direction, that means it's accelerating. That means there would have to be an unbalanced net force. Once it leaves the track is applying the force, but nothing else is applying the force. In other words, if you've ever been on a merry-go-round that was going very, very fast in a circle, If you jumped off, if the merry-go-round was revolving in this direction and you jumped off when you were at the top, you would go running that way, not that way. So why is it that the acceleration, turn the page, is inwards when all of you have been in a car and turned a corner and you felt that you were getting pushed outwards? Right? In fact, as a matter of fact, your grandparents may admit to this. Your folks aren't old enough. Your grandparents might be. Back in the days in the 1950s, before cars and before seatbelts were mandatory, cars had bench seats in the front. Some pickup trucks still do. And so if you were a young up-and-coming teenage boy, what you would do if you were going out on a date is you would get a bunch of surfboard wax, and you would wax down the bench seat where your date was sitting, and you would sit with your arm like this, and you would do a quick right turn, and she would come sliding across into your arm, and you would, oh, hi, honey, that's very nice of you, and you'd be, look what I did. At least that's what you would think if you didn't understand the physics of it. And as a matter of fact, that's not what was actually happening. Check with your grandparents. Your granddad might admit to it. We'll find out. Okay? What's actually happening is this. Your body wants to keep going in a straight line at a steady speed. That's Newton's first. For you to be turned this way, something has to apply a force on you that way. Yeah, it's the inside of the door. If you're in the passenger seat and you're making a left turn, the reason you feel like you're getting pushed out is actually the door is pushing you inwards to get you to move into a circle. And forces come in pairs, and so you think, oh, I'm getting pushed out. In fact, with that surfboard wax trick that I just told you, actually the girl was going in a straight line and the car was rotating underneath the girl. So although to the guy's viewpoint the girl was sliding across to him, actually what he was doing with that quick turn is rotating the car underneath the girl. She was going in a straight line and he was moving himself to intersect her path. So I wrote here, the push is an inertial effect. When we are turning the car, the friction with the road turns the car, and the friction with our seat turns our lower body, but our head initially has no inwards forces acting on it, so it wants to keep going in a straight line. So your body has to apply a force on the head, and your body thinks the reason you're applying a force on a head is, oh, I'm getting pushed outwards. From the point of view of the driver inside the car, this straight line motion seems to be outwards toward the passenger door if you're turning left, or turning right towards the driver's door. This is very important because many years of experience in the car lead many people, non-physics students, to think there is an outwards force. As a matter of fact, you'll even hear it given a name. They'll call it centrifugal force. Centrifugal force. I'd like you to underline it and then put an X through it. This is not a force, actually. Centripetal force is the force that's pushing you in a circle. Centrifugal force is not a force. It's your body's inertia, and it's your body having to exert a force against its own inertia to push it in the middle, but because your body has a backwards accelerometer, you think you're getting pushed outwards. So this outwards push is not outwards, it's in a straight line, and it's not a force, but actually just inertia or mass. Furthermore, vector analysis, which we did a few minutes ago, shows the acceleration is towards the center if you subtract the two vectors together by adding them tip to tail, but adding the opposite. If fighter pilots fly too fast into a loop, they can become unconscious due to a lack of blood flow to the brain. This is sometimes attributed to centrifugal force. What's really happening? Here's our pilot. There's our airplane. And we're going to exaggerate the diagram. So here's the pilot sitting in a chair. Something like that. Okay? There's my high-tech stick figure drawing. Here, you know what? I used a bad color because I want blood to be red. There's the pilot sitting in his plane. He's going to do a loop. So what I'm going to do is I'm going to focus on the blood in his head, right there. It wants to keep going in a straight line at a steady speed. It wants to keep going this way. Right here, the pilot's body is now like that. Where is the blood pooling up? Not in his chest. Where is it? Far away from his brain. So although people will say, oh, the blood left my feet, sorry, the blood left my brain, and that's why I blacked out. Actually, your brain left the blood. The blood didn't go anywhere. The blood kept going in a straight line at a steady speed. Your brain got pushed up and away. And that's how pilots can black out. Put your pencils down.